Alright, this example is about using what's called operator notation. Now the key thing to differentiation is that differentiating is an action that you're applying to something. Okay, so it's like saying, you're going to kick the ball or you're going to open the door. You're going to differentiate something. So differentiating is an action, and we show that we're going to differentiate a function by using an operator which is called the ddx operator. So if you have a function that's wandering around, wandering along merrily, x squared, and you say, I want to differentiate that function, what you do is you write d dx in front of that function. And a lot of the time you may see it written with brackets around it as well. That just shows that that's the function we want to differentiate. So this part here really tells us we're going to differentiate. This is the function we're going to differentiate. And this tells us the variable we differentiate with respect to. Now at this point you might think, well, yeah, obviously it's x because it's got x in there. We will start dealing with functions where you actually have the wrong variable down here, like dy, and there's no y's in there. We actually have to do additional work to make sure it's in a format where these variables match. So the key thing with a derivative is that your variable down here should match the variable that's in your function. So this would be a function of x to match the variable that's down there. Okay, so that's the key thing about a derivative. The operator is the ddx operator, which we apply to functions. So the first question that we're looking at here, we've got ddx outside of x squared plus 2x plus 3. That literally just means differentiate x squared plus 2x plus 3. We know that when we differentiate, the power comes out the front. We then take 1 off the power, so 2 will become the power of 1. Again, we actually have a little power of 1 there with an x, so when we differentiate the x, the 1 comes out the front and multiplies the 2. We get x to the power of 0, and the derivative of a constant is 0. Now you'll know that anything to the power of 0 is 1. So this is really going to cancel down to 2x plus 2. So derivative of x squared is 2x, and the derivative of 2x is 2, and the derivative of the constant is 0. So that's the derivative of that function. The next one, you've got ddx outside of, it's a sort of more complicated looking function, e with a little x squared going on. So that means differentiate this function. Okay, now to differentiate this function, we're actually going to think of this as a function, the exponential function, with a function inside. Okay, so what we're going to do, we're going to let u equal the function inside the exponential, so that's x squared. So we then have we'll let y equal e to the power of u. So we'll let all of this equal y, just for the sake of using the chain rule. So we have e to the power of u. We've let this thing equal u. Good old-fashioned chain rule, du dx, differentiating x is 2x, then dy du. Derivative of e to the power of u actually is great because exponentials don't change. It stays the same, e to the power of u. They do change if there's anything other than an x or a u. Whatever this variable is here, if there's a coefficient, it comes out the front. Essentially, the derivative of this function comes out the front, which we'll see in a minute. So, chain rule dy dx equals du dx by dy du. Doesn't matter the order, as long as the dy is on the top. Oh, excuse me. That should be a du. And the du is on the top and bottom, so they could cancel. So we've got 2x times e to the power of u, and remember that u is x squared. So what you might notice here is that the derivative of an exponential is whatever's out the front, the derivative comes at the power, the derivative comes out the front. So that's what happens always with exponentials, and I'll actually write that. I might leave that there, that's quite nice. I'll write that here for you. So just to finish off that question, so we have the derivative of e to the x squared is this answer, 2x e to the x squared. Exponentials are like trig, they never give up their power. They leave it there. It never changes, you don't take anything off it. X is the only one that's easily affected. Okay, the power changes. Exponentials, they don't. So the key result here is that if you have y equals e to the power of ux, the derivative of y is the derivative of u. Whatever the power is, derivative comes out the front, and the power doesn't change. So that's a great one to put in your notes, highlight it. A fantastic result. Ooh, it's not very nice. Move everything up. For you to know for your exponentials. All right, just put that there. So we can see now we've got one more left to do, which is the trig. Oops. And I'm just going to copy the questions onto the next page. So derivative of the power coming out the front for that. It's a really useful one. So the last question we've got here is a sine squared. And the thing you might notice here is, hey, it's not an x anymore. It doesn't matter that it's a z because the z is in there. They match. So that's completely fine. We can still carry this out. So we have c is d dz this time. So the derivative with respect to z of sine squared z. Just going to write that out slightly differently. D dz of, I'm going to put that in square brackets. Sine of z is all squared. So what rule might you use? Again, function inside a function. You see chain rule just gets used so much. It's just a classic. I'm just going to let y equal all of the thing that's in there just for the ease of doing it. So this is now u squared. Again, du dz. Why is it du dz? Because that's the variable that's inside u. So du dz, and derivative of sine is cos. This would then be still dy du, oops, dy du, which is 2 times u. Remember the power comes down the front. So we now have dy dz because we're trying to differentiate with respect to z, and that's going to be du dz by dy du. Du's cancel, so that gives you the dy dz that you want. And remember, you just multiply these two things together. And u is sine of z. So we have 2 sine z cos z, like that. And what that means for this question is that, therefore, the derivative of sine z squared equals 2 sine z, ooh, do that again, cos z. And for those of you that are really familiar with your trig formulas, you would recognise this as the double angle formula for sine of 2z. So this is actually sine of 2z, and that's because sine of 2x equals 2 sine x cos x. So that's your answer. So the final answer there is sine of 2z. So what we've done is we've shown that we can use the differential operator, d dx, or d dz, or dd, cat. It doesn't matter what it is as long as it matches what's inside the function. And then we've also learned how to differentiate exponentials as well. Derivative of the power comes out the front and the power stays unchanged. So that's the operator notation for differentiation.